Having established and grounded our understanding of two-body orbits, it's now time to look at orbit determination. And orbit determination encompasses not just fitting of orbits from data, but also planning of orbits. We can think about trajectory planning as a form of orbit determination because we typically wish to find orbits patching points in space. However, for the most part, people tend to think about orbit determination as a fitting problem, and historically, this is where all the basic methods of orbit determination originated from, trying to fit the orbits of naturally occurring bodies. And of course, this is where we get Kepler's laws. Those were based on fits to observational data. Most modern orbit determination, and especially that of Earth orbiting spacecraft, relies heavily on range, azimuth, and elevation measurements. So coordinates in the topocentric horizon frame for some local observatory on the ground, as well as some separation distance estimates. And those are provided by radar and LiDAR. And those measurements are, of course, only possible if you can get a radar or LiDAR return from the object, which typically you can't for more distant bodies and naturally occurring bodies and bodies outside of the solar system. So here we will consider the cases where range cannot be calculated, and instead you only have angle measurements, which is the case whenever you are using optical sensors and for all deep space objects. And we begin with Gauss's method. There's a really fascinating history behind Gauss's method. By the start of the 19th century, we knew about all of the planets in the solar system up through Uranus, and the Titius-Bode scaling law of planetary separations had been established, which predicted the occurrence of a planet somewhere between the orbits of Mars and Jupiter. And so astronomers were busy trying to find this body, and on January 1st, 1800, the Italian astronomer Joseph Cazzi discovered a planetoid that he called Ceres. Of course, at that point, nobody knew that it was a planetoid. The existence of the asteroid belt had not been established. And so he thought that this was a candidate for the missing planet that was predicted by Titius-Bode. Unfortunately, Ceres at this point was moving behind the sun, and astronomers were only able to get 41 days of observations, which covered an arc of 9 degrees. And at that point, nobody had ever successfully fit an orbit with so little of its arc explored with measurements. Astronomers and mathematicians attempted to use all of the mathematical tools available to them at that time to establish Ceres's orbit, but when it was predicted to come out from behind the sun and astronomers started making more observations, they couldn't find it. It was lost. And this became a huge internationally known problem with even a cash prize associated with its solution. And so in steps Carl Friedrich Gauss and decides to take a stab at it. And by the end of the year, he publishes predictions that lead to the successful reacquisition of Ceres. And in the process of solving this specific problem, he effectively invents an enormous swath of mathematical tools and numerical tools that we still use today. So, formally, Gauss's method is the determination of an orbit from 3 angle-only measurements. Consider 3 position vectors belonging to the same orbit at different times, denoted here as r p rel gt1, r p rel gt2, and r p rel gt3. Here we are effectively assuming an orbit about the Earth, but of course this method applies equally to any orbit about any central body. You just have to calculate the correct vectors accordingly. So we have these 3 vectors describing the orbit at 3 different points in time. And you are also taking measurements of them from a surface point on the Earth. So for each of these, you have the position of the object with respect to your observer location, but we now have the ability to calculate the separation of the observer from the center of the Earth at any time, and so we can make the vector conversions as necessary. So we will call these 3 position vectors of the object with respect to the center of the Earth r sub I, and we will call the position vectors of the object with respect to the observer location rho sub I. And Ri scalar will be the norm of r sub I, and rho I scalar will be the norm of rho. Assuming that this is a 2-body orbit, all 3 of these vectors must lie in the same plane, the parafocal frame of the orbit, and therefore the vectors are linearly dependent. So we can write for some scalar values c1, c2, c3 that the linear combination of r1, r2, r3 scaled by c1, c2, c3 must be 0. We know this from the basic physics of orbits, but mathematically speaking, we can also verify this by writing R2 crossed with R3 gives us an orthogonal direction to the orbital plane. And if we dot that with R1, we get 0, confirming that these must be linearly dependent. If we now assume that C2 is non-zero, we can write that is our linear combination, which equals 0, crossed with R3, leaves only the terms R1 crossed to R3, scaled by C1, and R2 crossed R3, scaled by C2, and this equals 0. And the R3 cross R3 term is itself 0. If we rewrite this, we get, so C1 times the cross product of R1 with R3 is equal to negative C2 times the cross product of R2 with R3. And in the same exact fashion, we can get this second expression, C3 times the cross product of R1, R3 is negative C2 times the cross product of R1 with R2. Remember that we can express any orbital radius vector in using f and g functions as a function of another orbital radius vector and velocity vector of the same orbit. And previously, we've thought of f and g functions as propagating the orbit forward in time, but orbits are fully time reversible, and so there's no reason why we can't use f and g functions to go back in time. And so I know that I can write R1 as some f function f1 times R2 plus some g function g1 times v2, and similarly for R3, I can write f3 R2 and g3 v2. So essentially, I can always express the position vectors at time t3 and time t1 as functions of the position and velocity at time t2. Without any loss of generality, I can take C2 to equal -1. Remember, this is just a linear scaling that equals 0, and so I can scale all of these up and down. If I set C2 to -1, I just have to scale C1 and C3 accordingly. Then I can write so we've taken our result where C1 is equal to negative C2 R2 cross R3 divided by R1 cross R3 as follows. We are positing that C2 is -1, so that this term goes away. And then we are going to replace R3 with the f and g function as functions of R2 and V2. And similarly, in the denominator, we'll replace both R1 and R3 with their f and g function values as functions of R2 and V2. And we can then take the cross product up top, canceling this first term, leaving only the G3 R2 cross V2 term. And finally, recalling the anti-commutative nature of the cross product, this is negative R2 cross V2. And so this entire expression instantly simplifies down to, in the exact same fashion, I can do this for C3 and get a very similar looking expression. So these coefficients, C1 and C3, can be written strictly in terms of the f and g function values for the propagation of R2 into R1 and R3. Recall now that we've provided ourselves with a method of deterministically evaluating the f and g values as series solutions. If we define sigma as the gravitational parameter divided by r cubed, then the f and g values can be calculated in series as follows. Because the intent of this method is preliminary orbit determination, and because the measurements themselves are intrinsically noisy, we don't need a whole lot of fidelity in our computation of these f and g values. We are looking for an initial guess that we can then refine. And so we are only going to take these series to second order. We are only interested in these terms up to order delta t squared, where delta t is some small time, because again, this method is targeting small time differences between the measurements. We are explicitly looking at the case where we have a bunch of successive measurements covering a small arc of the overall orbit. So what can we do with this? We take C1 is equal to G3 over F1 G3 minus F3 G1, as previously established. And we are going to replace each of these terms with the first couple of terms of their series solution. So every instance of Fi will be replaced with 1 minus sigma over 2 times delta Ti squared. And every instance of G sub I will be replaced with delta Ti minus sigma over 6 delta Ti cubed. And remember, we are defining delta T1 as T1 minus T2, and delta T3 as T3 minus T2. Again, following this idea that these F's and G's are mapping R1 and R3 to the center point R2. So we'll start by evaluating this denominator. So all we've done here is plugged in the first two terms of each of these series into each of the four terms of the denominator and written it all out. We are instantly going to drop everything that is of order sigma squared, because you will recall that sigma is mu over r cubed. So sigma squared becomes a very small value. So we're going to ignore that. And then we're going to take the rest of this and rewrite this as, so we are packaging up all of these terms and dropping everything that we're considering small. So everything order delta ti cubed and higher, and everything sigma squared and higher into these two expressions, delta T3 minus delta T1 and 1/6 of delta T3 minus delta T1 quantity cubed times sigma. Making the substitution for G3 as well, we can then rewrite the entirety of C1 as approximated by so this is our G3 numerator, and this is our approximation of the expanded denominator, where these are sigmas and these are sixes in the denominator of each of these two fractions. We rewrite this a little bit more, and it becomes, so we've just pulled out a factor of delta T3 minus delta T1 from all of these. And so we have this leading term, delta T3 times the quantity 1 minus sigma over 6 delta T3 squared divided by delta T3 minus delta T1, the whole thing multiplied by the reciprocal of 1 minus sigma over 6 times quantity delta T3 minus delta T1 squared. The reason why we've done this is because this gives us a form that makes it easy to apply the generalized binomial expansion. Remember, as an aside, the binomial expansion of the sum x plus y to the rth power is going to equal the infinite sum of r choose k of x r to the r minus k, y to the k. So in this case, we are going to apply the binomial expansion to this term, which means that we have x equal to 1, y equal to negative sigma over 6 times the quantity delta T3 minus delta T1 squared, and r equal to negative 1. Applying the expansion to second order, we thus find that this whole expression equals 1 plus negative 1 times our whole y term, and then everything else will be of order delta T3 to the fourth, or order sigma squared, and so we ignore it as we've ignored these quantities previously. So let's regroup. We now have delta T3 over delta T3 minus delta T1 times the quantity 1 minus sigma over 6 delta T3 squared times quantity 1 plus sigma over 6 times quantity delta T3 minus delta T1 squared. For our next step, we are going to multiply out this entire set of polynomials, and that will give us 1 minus sigma over 6 delta T3 squared plus sigma over 6 times quantity delta T3 minus delta T1 squared minus sigma squared over 6, and the rest doesn't matter because we've hit another sigma squared, and we will drop it because we're dropping all things of order sigma squared. And this is now our final solution. C1 is approximately delta T3 over delta T3 minus delta T1 times the entire quantity of 1 plus sigma over 6 times delta T3 minus delta T1 squared minus delta T3 squared. And we probably need a closing parenthesis here. So here we have rewritten the same expression and distributed out the delta T3 over delta T3 minus delta T1 over the parentheses and regrouped a little bit. And we will call this leading term A1 and this second term B1. And we can do the exact same expansion that we just did for C3. And I urge you all to try it on your own to make sure that you have the mechanics of this. And we get a very, very similar form, except with some negative signs, and the indices changed around, of course, and we will call this term A3 and this term B3. All right, fantastic. But so what? Who cares? We've done a bunch of manipulations and we don't seem to have gotten anywhere closer to what we really want, which is to use these things to establish the orbital elements of this orbit. Remember the basic setup of what we're doing here. We have three position measurements, or at the very least, we have the unit vectors of three position measurements of our object with respect to our observer location at three different times. We assume that we have the ability to compute the position of the observer with respect to the center of mass of the relevant central body, in this case, the Earth, at those three times. And so from that, we can get the position of the object with respect to the center of mass of whatever it's orbiting at those three locations in time. And for shorthand, we are calling these quantities rho I vectors and these quantities the r sub I vectors. And r o rel g t sub I we will leave as is. We've also established that there's a linear dependence between these three r sub I vectors. And the fact that we can write the weighted sum of this equal to 0 means that we can apply the same weightings to the summation of these two sets of vectors. And so we can write the weighted sum of the rows using the same C1, C2, C3 coefficients is equal to negative the weighted sum of the R O rel G vectors using those same coefficients. So we're going to turn this into a linear system. And we're going to package this as the unit directions of the row vectors. And this is now our fundamental measurement. We are measuring angles on the sky at three different times with respect to our observer location. And so this measurement, with each of these vectors being expressed as a column vector, packages it into a matrix A. This matrix A is then multiplied by this vector of C1, row 1, C2, row 2, C3, row 3 to recreate this left-hand side of this expression. And on the right-hand side, we have the three position vectors of our observer location with respect to the center of mass of the Earth times negative those three C coefficients. As long as A is non-singular, we can invert it, and then we can move it over to the right-hand side, which leaves us just this set of quantities on the left-hand side, and then this A inverse matrix times our three observer location vectors packaged together in its own matrix, and together this we will call the matrix B, and B is still being multiplied by the vector of negative C coefficients. Remember also that we posited that we can take C2 to be equal to -1, and we provided ourselves a method for calculating C1 and C3 under the assumption that C2 was -1. So because of that, we know that we can write row 2, which is here just being multiplied by a -1, as a single row out of the B matrix. So what we will get here are the elements of the second row of B times the A and B coefficients. And remember, we've defined the A and B coefficients as these terms within C1 and C3. And we will call this whole thing D1 and this whole thing D2, and D2 is also multiplied by sigma. Almost there. We have just one more step to take. Remember, R sub I, which is the norm of R sub I vector, has to be equal to the norm of rho sub I vector plus R of O rel G at the time T sub I. So we can apply the Euclidean norm and write that is R sub I will be the square root of the quantity rho sub I squared plus 2 times rho sub I multiplied by the dot product of the unit direction of rho sub I with R of O rel G at the time T sub I plus the norm squared of R of O rel G at the time T sub I. And that means that the distance R2 squared will be equal to quantity D1 plus D2 sigma squared plus 2 times D1 plus D2 multiplied by rho hat 2 dotted into R O rel G at time T2 plus the norm squared of R O rel G at T2. Because sigma is mu over R cubed, and in this case R2 cubed, substituting this back in gives us an 8th order polynomial in R2 as follows. So that was a lot. So let's summarize. We start with 3 angles only measurements of some orbiting body, and we call those things rho sub I. We have the ability to calculate the unit vectors of rho sub I, and we are looking for position vectors in order to track the distance to the body and get a preliminary orbital fit. We will shortly explore another method that allows us to use any three position vectors to instantly get the orbital elements of the body. So getting these r sub I vectors is equivalent to fitting the orbit. We go through this arduous derivation process to get an approximate approach to finding these r sub i's given the rho hat I measurements. And at the end of the day, we end up with an eighth order polynomial that gives us the distance, the geocentric in this case, but it's with respect to whatever central body you want it to be, distance of that intermediate measurement. And this eighth order polynomial is a function of the various coefficients that we've developed and quantities that we know, such as the offset between the observer and the center of mass of the central body at each of the three times. So you effectively solve for any positive real root and then recalculate the sigma value, all of the C coefficients, the A inverse matrix, the B matrix, and you go again and again, and eventually you get all of the rho sub i's. Gauss originally developed this methodology to track Ceres, a heliocentrically orbiting body, and this still works best in applications to interplanetary trajectories. The angles between observations for this, especially due to the various approximations that we made in finding the C coefficients, should be small, and ideally smaller than 10 degrees. You can do better with better approximations of the F and G series, but you're always limited to the first order in sigma because you would need the derivatives of R to get to the derivatives of sigma, which are necessary to go to higher order. And so there's just an overwhelming body of specialized literature out there on orbit determination building directly on top of Gauss and extending the methodology to work better for larger and larger orbital arcs. But all of it has its grounding in this first initial analysis.